record on the computer. And this one I'll put on the site in here, along with the other videos, not to confuse you. I'll put them by date. All right. So this is 13. Should I wait a couple more minutes? So these are 4 data sets we're going to discuss. Back to my controls. You see the power I have to mute you. Okay. Don't forget to mute. The music selection is not bad either, though. A little entertainment. All right, so I'm going to start at 7 minutes after. So, oh, somebody in the chat. Oh, let's put the chat up here too. Okay, we have the chat. We have me. We have the participants, so maybe I'll cover me. Oh my God. Oh, I can put me here. If you want to see me. Okay, I can't put it all. All right. All right, so we're going to talk about data. Once you have a set of data, what do? You have data is a plural for data is a plural. Okay. If you have one data point, it's called datum in English, but anyway, so data is a plural. So data, once we have all our data, we have to observe it. We need to look at it in a way first. And the way that we look at it is going to be an image, a graphical image. Now we have some options to choose from on what kind of graph we're going to make, and we're going to talk about graphing. What are called distributions. Distribution. So the distribution depicts the variable, and it shows what values the variable takes and how often it takes those values. All right, so we want to display the distribution, and we want to keep a few things in mind. Let's say, you want just enough detail, just a tip, just enough detail to see any pattern or anomaly. So a pattern. You want to see if you can identify a pattern and any anomalies, anything curious that's away from the pattern. And once we've done that, we can then talk about summary statistics, because the pattern will determine what kind of summary statistics are appropriate. Okay, we'll get into that. So first, you notice I put this first because it's first, graph. graphically display a distribution to help best reveal its features, including its regularities and curiosities. But not too much detail, and you'll see what I mean. If you put too much detail, you can't see anything. And then, depending on the 5 features of the distribution, which we'll discuss, so we're going to discuss what's best, the 5 features. A different set of summary statistics should be reported, okay? So this is the document lecture notes. And there's another document called sample problems. Now this document is where we have some sample data sets. Anyone like baseball? Are Haitians into baseball? This is a baseball example, American baseball. So in baseball, in the history, there were 2 recognizable stars of baseball. One is Roger Maris, it's more recently, and then there's Babe Ruth. Now, Roger Maris held a single season home run record, so it means that he got the most home runs between 1961 and 1998. There was one season where he got the most home runs that any baseball player had by that time. Okay, so it was 61 home runs. And he held that record for a long time until recently. And while Babe Ruth had a longer career and held on to the record until Maris got 61 to beat him by just 1 home run. Looking at these numbers, can you answer the question, who is the better baseball hitter? Can you answer the question here? What do you think? You can put in the chat, you can talk to me. And why? So the variable is home run hits. That means they hit the ball and they ran around the diamond. I think that's what it means. So we're comparing not only these values, but the career. You think Maris is better?
Apparently, because she plays for 15 years.
You mean, no, this one is Maris and this one is Ruth.
All right.
15 years,
Wolf.
yeah.
Okay,
this
Wolf.
is Babe
Okay.
Ruth. This is Roger. They're both, yes. And this was in the 30s and 40s. I think 30s and 40s. And this was in the 60s.
It's because he has 61.
So Maris, if you look in the record books, he held the record for almost 30 years, having the most home run hits.
Mm-hmm.
But who is the better baseball player? Would you say? Would you say Roger Maris because he got 61, or like Jean
For 10
Knockout?
years. Mm-hmm.
I think it's
It's
Wood.
Mary.
Okay, put it in. Put your vote in the chat. Put your vote. Who is the better baseball player? Ruth or Maris?
I would say Wolf,
Ruth.
because he plays for 15 years.
Yeah.
I'll say Root too. He has more experience.
Okay.
Yes.
Okay. What about the numbers? Not just the career, but the numbers. Look at the values. The magnitude. What would you say looking at the numbers?
It's the
I could say
magnitude
that the majority of the numbers of Root are
and the number of players, yes.
So they're higher, right?
higher. Yes.
Higher numbers, more, more
Yes.
consistently higher than Maris.
Exactly.
Okay, so I will agree with you that even though Roger Maris had 1 year that was higher than Ruth, in general, as a baseball player and in terms of career, Babe Ruth was a stronger baseball player consistently. I think the key word is consistent, right? It's consistent. It's a more consistent. So if you were to bet, money on Babe Ruth winning a game, you would feel more confident. You'd be more confident in Babe Ruth hitting, being a successful baseball player than you would be in Roger Maris if you had money, right? If you could bet on either of them, you'd rather bet on Babe Ruth, more reliable, more consistent career in terms of home runs. So we know the answer. Now we have to put it in a systematic way in writing. That's what we have to do next. And I'm going to show you how to do that. Let's see. Okay, let's go through the 4 data sets and we'll just talk about a couple of them, okay? That's the first one. The next one, here you have the data that I'm going to show you represents 50 consecutive shoppers and how much they spent in the store. Looking at this as a marketing consultant, what does the spending of these shoppers tell you? And how can it help improve your marketing strategy? Okay. So I'm going to show you the data. The data, actually, I'm going to show, it's better in the other set of notes. Hold on, over here. So I have this data demonstrated here. So this is the other, I go between the 2 documents. So here is the spending data. Every time I change, it shrinks the display. Okay. Here you see all the spending. I put it in order and I made a graph here. So what I want you to do is first tell me how I made this graph, or account for this graph, how it was made, and then we'll talk about what it means, all right? So let's see. I'm going to try and display this at the same time. I'm going to take this picture up here. So this is called a stem and leaf plot. So tell me, how did I make this graphic? Oops.
You take in account the list of the price from the minimum to maximum.
Okay, so the first value, it represents this number. So I've taken the data and I put it in order first. Okay, so this is all the data of the 50 shoppers put in rank order. Then I do something with the number $2.32. I don't care about the decimals.
Okay.
I just make a plot with the dollars. Why did I do that? I rounded, right? Yeah, I rounded.
Yes.
How do you say it in French? Rounded.
Arrondi.
Okay.
Yeah.
Arrondi. Okay, so we rounded the values and put them here. Let me make this one just a little bit bigger. And you see, so 232 becomes just 2. And 661 becomes 7. And 690 becomes 7. And 804 becomes 8. And 945 becomes
9.
Very good. Okay.
9.
So you get the idea. So we round. When we round, we find our graph. And I'll show you how the graph arises if you don't see. The graph shows enough detail, but not too much. Including the cents will be too much detail and we won't see any patterns. All right, so we want to just, we want to combine the data like this and show this degree of detail. So what happens here now? The last value is 6949. What does that become?
69.
69, right. So that becomes, so 69, it has 2 digits. So what it means is all the values have to go into my plot, my stem plot, with 2 digits. So the stem is the first digit and the leaf is the second digit because these are just 2 digits. So for the first value, 2, the first digit is really 0, 2. The next value is 7. Now notice something is funny here because I'm dividing the data in even intervals between 0, 1 and 0, 4. So all the values from 1 till 4, so 1, 2, 3, 4, wait, no, I did that wrong. I'm gonna go till, it's gonna have to be 0, no? Yes, it has to be 0. $0, so 0, 1, 2, 3, 4. So there's 5 values. And then 0, 5 to 0. What would be the next class? Oh, I blocked. Let me unblock this information. So this is called the class or the bin. So all the values from 0 to 4 fall in this class. In the next one, the values 0.5 to 0.9. So 5, 6, 7, 8, 9. That's 5 possible values will fall in there. The next class, so it looks like so between here and here are the first 5 values before we arrive at 10. The next category or the next class begins 10. It will go from 10 till 14, and then the next one 15 to 19. So notice I take the first digit and make it the stem. The second digit is the leaf. So first we have 2, next we have 7. 7 goes here in the next class. And the next value is also 7. And then we have 8 and 9. So all of these need to fit. 7, 8, sorry, 2 7s. 7, 7, 8, and 9. They fit there. You see? 7, 7, 8, 9. Then the next class, the next value is going to be 10. That's 10. This one is 11, and this one is 12.
How do you get the classes? I'm a little bit confused there.
Okay, so the class is, so something, usually like in this class, I will tell you, I will advise you how to make it usually, right? Or I'll give it to you. So where does it come from? It comes from me, where I want them to, they must be equal in their content. So they have to be, they have to have or contain, it has to be an equal length interval. So this is 5 possibilities. This is 5. These are each 5 possibilities, right? So that's where they come from, that I'm dividing the number line into the first 5 digits, the second 5 values up till 10, and then we begin 10. The key is that the first digit is the stem. So that's why I have to begin with a 10 here. I couldn't go up till 10 here, otherwise this 0.5 to 10 they wouldn't share, all these values wouldn't share the same stem. That is a problem. So where does this come from? It's just my plan to divide the number line into classes. And I'm going to show you, if we do it another way, you'll have a different graph, and we're going to talk about that, okay? So questions, any other questions? Or did I answer your question? If I continue.
Yes, thank you.
Okay, if I continue, we have 10, 11, 12, and then this one becomes 13. And this one 13, and this one 14, and this one 14, and this one 14, and this one 15. Okay, so what do we have then? So we have a long string, you see. This is 10 because you have 1 and 0. The next is 11 because you have 1 and 1 makes 11. The next one is 12 because you have 1 and 2, that's 12. Then 13, 1 and 3 is 13. And then 13, 1 is 3, 1 and 3 is 13. and then 14, 14, 14. So those are the numbers that correspond to these. Questions?
Sure.
Yes. Tell me.
In this case, it's not about observation, it's about price. Or
So in this case, it's the spending. Yeah, this is a price. That's right. We're observing how much they spent. Okay.
okay, I would
So,
say it's not about frequency.
okay, so frequency. So let's see. So first of all, let's finish. Does everyone see how I made this first of all, and then we'll talk about frequency. Everybody see how I made this? Now, what I'm going to do with this, I'm going to turn it like this. I can make it.
I have a question. Why we have 2 stem 0 and 2 stem 1 1? Why we don't continue with the 1 with the 0 in the same line?
Okay, so this is very good. So why don't we just go? Let me know if this is your question. Why don't we go 0 to 09 and then 10 to 19? Is that your question?
Yes. Yes.
Yes. So let me show you what that looks like. So I did that here in the other document. I think I did it here. All right. So here are the two drawings. This is called, they're both stem and leaf plots. Hold on, let me make it bigger again. I lose my potency. Okay, so this is going by 5. And this is going by 10. So it's different. And I'm going to explain to you why I pick this one over this one. Now, unless I tell you what to do, you should, in practice, make both and decide in a systematic way which one you will pick. I'll show you what I mean about systematic in a moment, okay? So we could do it. It's not wrong, but one is better, right? So when I'm looking at this, I can, as I said, I can turn it on its horizontal axis. And I can put a yellow curve around it. What am I doing when I do the yellow curve? What am I insinuating? What am I doing? Oh, I lost the whole thing. No. Sorry. Just went over the yellow curve. So I could, without having any other knowledge, I want to summarize the shape. I know there's detail in here. First of all, I eliminated the detail of the cents. I made it dollars. I rounded. Next, I don't need so much the detail about the values inside. I'm only interested that the values here are a frequency, right? Your classmate mentioned frequency. This class is a very small frequency. There's just one observation. This class has 4 observations This class has 1, 2, 3, 4, 5, 6, 7, 8 observations, and this one has the most. So all I care about is that the number of observations. I treat all the values in one class as though they're the same, and I smooth the curve. Either I can see it like, let me use this. I can either see it like this, or I can see, I think it is really like this. Which one do you prefer, the blue or the black? And what are the implications? So maybe you don't know the
Black
answer
one.
right now. You like the black one?
Yes.
Okay. Anybody like the blue one? So let's talk about that, all right? So what am I doing? When I'm smoothing, what I'm saying is, if I had more data, remember, this is just a sample. This is a sample of 50 shoppers. If I had more data, I believe that the pattern would remain like this, the black one or the blue one. This is an idea. The smoothing is saying, if I had all of the data, even the population, if I had the full population, I believe it would still have this pattern, regardless of the numbers inside. I believe the pattern would be like the blue or the black. Now, if you like the black, you have to tell a story, you have to explain it. So how can we explain the black? Hold on, let me mute someone who is forgotten. So we need to tell the story that there's some shoppers here. Look how much these people are spending. These people are spending between $0 and $24, right?
24, yeah.
And these shoppers are spending between
26.
like
26.
25
5 to
to
40,
49.
$49. Or we can include this one here, even though it's low.
52.
So 50. Yeah, we'll say the
55.
whole class, 55. Yeah, we're
55.
talking about the class, 54, right? 54 to be precise.
Yes.
54. But then there's a few here that are spending 60, from 60 until $69. So it's in this group here, like 6 customers, like up until here, 6 of these customers, it takes 6 of these customers to spend as much as one of these customers over here in the high group. Okay, so these are different classes of people, different groups of people that you might want to talk about. Maybe, and this would be for further research, maybe they're divided by income. Maybe these people make less money and they spend less money than these people, and these people make less money and spend less money than this group of people here. So this might be low, middle, and high income, maybe. Or maybe these customers are not residential customers. Maybe they're business owners, and maybe they're commercial business owners, or they have a restaurant and they're buying some groceries, because this is a grocery store, right? So they're buying some things, they're buying alcohol that tends to be more expensive. So these are either divided by income or some other characteristic that's worthy of investigation. And because I think this group is different from this group, I want to find out what are their needs and what are they spending and who are these people. Maybe I will offer more products for these people because these people spend a lot. So it's important to use 3 because I see 3 peaks. 3 peaks. And I want to maintain those 3 peaks. So, and I believe if I use the black curve, I believe that, well, maybe I'll write it in black so you can differentiate. I believe if I had observed more shoppers, I would still maintain this pattern. Now, what if we didn't do it this way? If we didn't make the stem and leaf plot this way and instead made the plot like this, we wouldn't even see that pattern. Notice. How many peaks in this data?
Five.
No, 2. Trying to do it smooth, but it's not. Just 2. There's 5 classes, 1, 2, 3, 4, 5, 6, 7 classes, but there's 2 peaks, 1, 2. And so because of that reason, well, because of the reason that I want to discuss and interpret this distribution with 3 peaks, I choose this distribution going by 5, a length of 5 in my classes, as opposed to a length of 10, okay? So this is where people talk about statistics. If you hear people talk about statistics being, you know, how you can lie with statistics or manipulate statistics. The truth is, I'm showing you both are possibilities, taking the data and representing them in 2 different ways. But it depends what you want to say about the data, okay? It depends what you want to say and what support you have for your statement. So let's see. We've decided then we're going to stick with 3. So we're going to make the drawing, and this is called, to say specifically, this is called a split stem and leaf plot. It's split because the intervals are
by 5.
Yeah. Let's say it are not by 10. Okay.
Teacher, can you make it bigger, please?
Oh yeah, yes. I forget that it
Thank
shrinks.
you. Thank you.
There you go. All right. So so it's split stem and leaf plot, and it's split because the intervals are not by 10. If I could even do this by 2. I could go by 2. I could go by a different division, but I'm going to pick to go by 5 because I like the way it looks, and I want to explain, I want to emphasize the 3 peaks. All right, so this is the graph. This is the graph I choose. based on this graph, then we need to start summarizing statistics. All right, but I'm going to wait. I'm going to pause on that. I want to show you the other data sets before I continue. So we have, oh no, not here. So the other data sets are
Teacher,
yes.
you start counting peaks after each row.
Say that again.
Are you
Sorry, I think I lost you. I don't know why it keeps going small like this. Somebody asked about 69. Yeah, this is 69 because that's the end of the interval, 69. Sorry, you can write your name and sorry, your question in the chat in case I lose you. Okay, so there's the data sets are in the document called sample problems. I like this display, but it keeps shrinking. All right, so in the sample problems document, this is the data. So this was the first data set with the baseball players. This is the spending data. But here it's just the raw data. They've not been put in order. The next set of data is known as the Newcomb data. And then the last data set is this one here. Okay, so let's look at what is Newcomb data. So oops, I went out. Newcomb data is here. Again. Emmanuel, where do you find the intervals 0 to 24? In the last graph? You mean here?
Yes,
All of
teacher.
these.
I don't understand where you find those intervals 0 to 24, 25 to 54, 60 to 69.
Well, what I'm trying to say is this class here, you see, I put them up here. So this one here, it runs. This one includes all values 0, 0 to 0, 4. And this one, all values 0, 5 to 0, 9. And this one, all values from 10 to 19. And sorry, not 19, 10 to 14. You see? So all the values that are in between here go in this group, this class. The values from 5 till 9 fall in this class. The values from 10 to 14 in this one, and 15 to 19 in this one. I mean, you can confirm with what we were doing here, putting the values somewhere. They were transferring this way. And so if I keep going, this is 20 to 24. So all of these together, I included all of these in one peak. So that's why I said 0 to 24. write it like this. And then this one begins 25 till 54. And then there's a gap here. And then this one begins 60. You could say 60 or 50 or 55. You could just say 55. 55 till 69. I don't remember what I wrote. So what I'm doing is showing a peak in this range down here. I hope that helps. Okay, so what was I saying? I was going to talk about the other data set. We'll come back to this one. We'll do more details. I just want to explain the other data set and graphing, okay? So graphing, this is, so this is a representation. Let me make this bigger again. Once again, it's always a downside to my methods. So this is here, Newcomb's data. And there's lots of data. You see there's 66 points, data points. So what do you think? You notice the values are very similar, you see? Very similar values. Very similar, except over here. So I have to tell you where the data comes from to help you understand what we're looking at. This was the data that was collected by a scientist, Newcomb, who attempted to measure the speed of light. Now, the measures that he took of the speed of light were very similar, which you would expect. You would expect that the measure would be similar because the speed should be precise, except maybe some variables create some variation. But it turns out, if you were to make a stem and leaf plot of the Newcomb data, it would look like this. There would be these two observations that are apart from the greater pattern. So when we see something like this, when you see an anomaly, you need to investigate. Was there an error? So maybe first, we're going to refer to those as outliers. These are outliers. They're observations that are away from the pattern. You need to investigate and determine if there was a measurement error. Maybe someone wrote a value wrong, or sorry, measured it wrong. So this is actually incorrect calibration of instruments. So it turns out that these numbers are actually a variation from, I wrote it here. Let me see what I tell you. It explains here. Light travels fast, but not instantaneously. Over 100 years ago, Simon Newcomb repeatedly measured the time in seconds that a light signal took to travel 7.4 kilometers from his lab to a mirror at the base of the Washington Monument. As a measure of the speed of light, he would then divide 7.4 kilometers by the approximate time it took to travel the distance. The speed of light will be measured in kilometers per nanoseconds, where there are 10 to the power 9 nanoseconds. Anyway, the point is the data represents any deviation from 24,800 nanoseconds. So the data that I'm showing you begins with 24,800 and whatever the number is that you see. Okay, so it was this was his methodology. This was the methodology he used in measuring the speed. And you can't see that. This is his methodology. And it's possible because there's so many variables. He has to have the mirror sitting properly. He has to shine the signal. He has to do it at a time, you know, and record the moment that he sends the signal. And then someone at the base of the Washington Monument is also recording the time. So all these instruments and the individuals recording need to do it properly. Maybe they made a mistake. So this numbers could be the result of a measurement error. They could be the result of a data entry error, that's something else, or a transcription error. So a transcription error going from his notebook into wherever he was, you know, copying his numbers, or anyway, there could have been some sort of error in the in operating the methodology. Or it could just be, it could be an anomaly. There could be a paradigm, we'll refer to it as a paradigm shift. Maybe something happened to cause that different number, and you'd have to investigate. In this case, it turns out when you look at the data, let me show you. If you take the data and you plot it, here we plot a different kind of graph. Do you know the name of this graph?
It's not histogram, or
That's right. This is called a histogram. And we usually use a histogram it's better than stem and leaf when you have a lot of data. I'll just say more than 50 values. So when you have a lot of data, you use a histogram. But I want to ask you, what do you gain and what do you lose? So what are you going to compare it to? Compare it to the drawing above. If you look at the drawing above, what do you gain and what do you lose?
So with the histogram, we can see the peaks very clearly.
You cannot, or you can?
You can.
You can see the peaks. Ah, okay. You can see more clearly. Okay. You can see the peak more clearly. Here, well, it definitely is more attractive, right? It's cleaner, it's neater.
It's more visual. I'd say it's more visual than the other one. It's more informative.
Okay, it's more informative. So what is a disadvantage? So mostly it's an appearance, right? It's mostly the appearance and the ease, because if you had more data, look, you would be off the page. It's not, you know, it doesn't look good. It doesn't, visually, this is much more appealing. And the peak, do you really need to go off the, you know, off the screen to make a point? No, you have more control in the histogram about your drawing, so you can make a better drawing visually. All right, so what do you lose? What's a disadvantage? You understand it's the same idea, right? Because I have intervals, so it's similar. What do you lose?
Let's say precision.
The specific data.
The specific values, very good. So you can't, you lose the data, you lose each data point, right?
Yeah.
You don't get to see it anymore. And sometimes you could care less. Sometimes you want to know. You want to say, are all of these values 40, or are they all, you know, a smaller value? You don't know. You don't know if these are all the high end or the low end of the interval. And that makes you have to guess. And it's nice to be able to see all the data here. I mean, you could then take the graph and appeal to the original data, but when you're presenting a report, you don't give the reader, the audience, all of the data, you just give them a graph. So it's nicer to present all the data, but when it becomes intractable or you know, you can't put all this data in a page if it goes off the page. It's not feasible. And if you make the numbers too small to fit them on a page, no one can read them. So in terms of visual appeal, this is better, but you do lose each data point. And if you wanted to be able to demonstrate anything about the data, you'd have to add another bit of information. This is not sufficient. Okay, so, all right, so then what happens now? What do we say about these? What do we do with these values that we determine? Let's say we determine that they are outliers. Now, how do I determine that? Sorry, not outliers, but they are measurement error. So here's the data in order of measurement. So this is my defense in eliminating these values. Now, you should never eliminate outliers unless you have a good reason. All of the data is up here, but we have these two values early on in the experiment or in the study. Early on in data gathering or data collection, errors were made. You could argue these were measurement error. So these errors were made early on in the process before the methodology or the methods were perfected. So in this case, we have an argument that we can eliminate or we can agree that these values can be eliminated. Now, if this was your study, you should keep a record of the values you eliminate, but don't use them in your analysis, okay? You should make a note, you should rationalize why you eliminate them, and then once you eliminate them, you would redraw your graph. And notice what happens. A lovely, smooth, what we call symmetric distribution emerges. Like it's smooth, very nice, like that. One peak, nothing strange, nothing unusual, very predictable. We'll talk more about that in a bit. All right, so this discussion was to emphasize that once you see a pattern, you can look at the anomaly. You have to explain the pattern. You have to explain the pattern before you accept the graph, okay? In our case, we had a graph over here, but it was not acceptable. We don't think these values are correct. In fact, we have this evidence that those were calculations that were made early on, likely as a result of measurement error, so we can drop them. So we agreed to eliminate these values and then redraw our graph. So I'm going to teach you how to make a graph, and we'll talk about that as well. So that's the third type of graph. What is the third? The second. So we did stem and leaf. We talked about histogram, and I'm going to show you how to draw that. And then there are these. Does anybody know what these are called?
Mustache.
Mustache. Is that how you guys call them?
Cap
It's true.
mustache.
We call them
Mustache
a
du
box.
chat.
Yeah, that's what you guys call it. Interesting. So we call it a box plot. So the box plot is a graph that's actually made up of statistics. So we actually need the statistics to draw the box plot. So we're going to get back to that. Box plots are used for two things. To compare distributions side by side. And you use them when distributions are skewed. In other words, not symmetric or asymmetrical. And I'll explain that as well. So most of what I'm saying, well, you will find in the videos that I've already made, but I'm talking about this with you here. And then you have to find the time to review my videos, these videos, and the other ones already online. Okay, so what is this data? This data represents the, let's see, let's go back and read what it represents. I believe I explained it here. So what you have here is on this page here. The following table shows the magazine laboratory test results for calories in a number of major brands of hot dogs. There are 3 types: all beef, meat, which is mainly pork and beef, but government allows up to 15% poultry, and poultry. So beef, meat, which is a mix, and poultry, which is chicken. The question is, are there any systematic differences among the 3 types in terms of calories? So this is the research question. This is the this is the data. Here are some statistics for the beef, the meat, and the poultry hot dogs. And without going into the statistics too much, what do you see? If this is the legend here, by putting them side by side, how can you comment? Without knowing anything about the statistics or the numbers, how do you comment on the graph? The variable is calories.
Min max.
So which type of hot dog has less calories?
Poultry.
Poultry.
Okay, so that's all I wanted for now. Just this is lower, right? This curve, this box is lower. So we're going to
This
talk
box.
about how to create it, but the green box, which is poultry, is lower than these, and the scale goes from low to high on the vertical. Okay, so that's a box plot. So let's go back now. So those are the 4 data sets that you're going to study and review in this document. I want to go back now and look at the statistics for the first, well, for this one. So I'm going to go here and we're going to talk now. We have a graph. We chose this version of the graph. So we chose this version of the graph, the black curve, not the blue one. And now we want to make some statements. Let me take it with me. See if I can take it with me. I'll get another one. Okay, so this is my stem and leaf plot, split stem and leaf plot. And you know what? Let's actually, I'm going to do it for the first data set. Oh no, let's start here. I'll do this one and then we'll go back to the first one. So let's see, what did we do? So we decided I want to put it like that. So we can put it like that, and we can do the smoothing. smoothing, and we believe there's 3 groups. And now we want to summarize. And how do we summarize? We summarize with the 5 features of the distribution. The first feature is the shape. You need to comment on the shape of a distribution. What shape is this? Is it symmetric or skewed? And if it's skewed, is it skewed right or left? What is symmetric? Symmetric would look like this. That in the center, from the center position or the center value, you have a mirror on the other side. So this is roughly symmetric. What does it mean? Symmetric means well, say regularity, but we say most of the values are around the center, and you have just as many values higher as you have lower. And you have just as many values much higher as you do much lower. It's a balanced distribution. Right? So remember, each of these here are classes, and we're counting the frequency to make the height. That's how we made this here. There's actual values underneath that you can visualize. And there's just as many values on that are lower as those that are higher. So if this filled in with values, you'd have just as many here as here, okay? Now, our case is not like that. In fact, this one is, you could have symmetric with 2 peaks or 3 peaks, but that's not the case. I could have, this is roughly symmetric too, right? Do it again. It's hard to get it perfect. So this is roughly symmetric. This is also has a center. And what I see across the center is balanced. I have just as many observations here as I have here. Okay, this is also symmetric. So it's not about the peaks. It's about the balance. So we call this kind of distribution where you don't have that, we call this distribution skewed. So for our case, it's skewed. And the direction of skewed is going to be skewed to the right. It means that there's only a few observations that are high. There's only 4 observations that are higher than the other 56 observations, 46 observations, okay? So we call that skewed to the right in our case. I'm gonna move that here. to remind you. So that's the first thing. Now that we have the shape, and you have to do it in this order, because once you have the shape, you can go into the second feature. The second feature is the center. So I've been talking for an hour and a half. You want to take a break? You want to take 5 minutes? Just realized I'm talking for an hour and a half.
Yes. Yes.
Yes, 5
Okay.
minutes or 10 minutes?
About 10.
Okay, 10 minutes. So I'll see you in 10 minutes and we'll continue. Bye. Okay, I'm back. We're back. We're back.
Okay,
All right, let's continue.
I'm there. I am there. You can continue. Let me see how many. Yeah.
Okay. So center. Center. The center of the distribution what we're trying to capture when we talk about center is more like expected value. For instance, what do you expect the next shopper will spend in the grocery store? What value would that be? If you just looked at the graphic, what amount would you suspect that a shopper would spend in the grocery store? If you were to bet, wager, what single
19.
value?
Between 20 and 21.
20.
You
You like this one here in this group?
Yes, yes.
Okay, anybody else?
I said a group before that one.
You think this one?
Where's the
Okay.
peak?
Okay.
Yes.
Mhm.
Okay. So you want to find the expected value. You see there's lots of observations here, and that's why you like
15.
that one. You see lots of observations. However,
15 is like 1, 2, 3, 4.
that's 15 here. That's the one you like?
Mm-hmm.
Okay.
Yeah, because I see it a lot
Many
of
times.
Many times.
Many times. Okay, so we have to do something. We have to balance out our expected value with the reality that we do see a lot of observations in here. We see many 15s, but the fact is there's quite a bit of variation over here. So what we want to do is get a compromise between these two. You know, this being the mode of this peak. So each peak has a mode, like a center. So this one has this peak. This one, I guess this would be, so if I was to draw, you know, this would be
Where the peak here is the center,
that's right.
where I can look at it, the center.
Yeah, so those would be the three peaks, right? This one, I'll include this
Between
one
the
and
three
this
peaks.
one. So you want
Okay.
so you see like three peaks. So if you have no way to measure, if you don't know yet how to measure visually, you think it shouldn't be this one and it shouldn't be this, but it's somewhere in between. So I'm not going to make it this one. So there's actually a measure that takes us in between. So let's talk about this a moment, okay? I want to spend some time on this topic about the center. And there's three possibilities. I'm going to go back to the notes that are here. No, not this one. Where are the notes? Oh yeah, these are the notes. These are the notes. So here we have the discussion in the notes. So first we talked about the shape, right? And the shape can be symmetric. Oh, let me make this larger. The shape can be symmetric, where it's balanced through the center, It can be right skewed, like the one we discussed, or the one we're talking about, or it can be left skewed. And I have some examples about symmetry. Symmetry occurs in the natural world. Often you see, if you look at heights of individuals, they form a symmetric distribution. Most people are a certain height of, well, of a particular gender. So women are a certain height, some taller, just as many shorter, and then there's a few much taller and just as few much lower. So it's balanced. So that's true for height, that's true for weight in adults, very symmetric. When you see something like this, a skewed distribution, most of the values are around here, but then there's a few extreme or high or large values. Income is an example of a right skewed distribution. If I was to plot income, there's always the, you know, people talk about the 1%, right? Or the 1% of the 1%. Very, very rich, that create a skew where everybody else is down here. And for left skew, how can you see this? So most values are high, but there's a few really low ones. I use the example of grade school completed. Most people finish 9 or 10, right? But there's a few that don't finish anything. Maybe they have some sort of challenge in learning that they do not advance, right? Or they have a handicap that prevents them from learning. So those are, now that you know what's under the curve, you can understand my discussion about the different kinds of variables that would look like this. Okay, so that's the shape discussion. We call this symmetric. This one is right skewed because there's a few values on the right that are high. And this one is left skewed because there's a few values on the left of the regular number line that are much lower than the rest. When we talk about center or the expected value, we're going to differentiate between, and I'll take the one, this is our example here, kind of. So we're going to talk about this spot here. The observation class here is known as the modal class. Sometimes you talk about the most frequent observation, but we just refer to the class where the most observations occur. So that's the modal class. We talk about mode. We're more interested in the modal class, where the class with the most observations. So this is called A, would be mark the mode. C and B are other measures that we use to summarize the expected value. It's usually the case that this one is the mean or average. The mean or average is a calculation that includes all of the values summed and divided by the total number of values. That's an average that most of you, I think you all know what an average is. That average includes every single value in its calculations. It means that it will also include this one, or the few up here in the extremes. As a result, it is closer to the extreme values than the compromise between the mode and itself. In between here is another measure, but let me talk a little bit more about the mean for a moment. So the mean is actually this, it's a measure of center of gravity. It's the balancing point of this distribution of observations. Okay, it's the balancing point. Now, it's not going to balance, this distribution, if it's right skewed, is not going to balance over here. It's not going to balance over here by the mode. It's going to balance somewhere in between, right? close to the mode, but also balancing off the weight of this long, long tail. All right, so the mode will give you that measure. I mean, the mean, sorry, will give you that measure. The average will give you that. So the average actually balances out this space here with this space here. It's the values and the number of them in total is stretched out on this end. So that's what the average gives you. So back to this. The number in between the average and the mode is known as the median. The median is also called the 50th percentile. Does anybody want to explain what that is? So 50th percentile is the observation where 50% of the other observations are on the left, and then that makes it so that 50% of the observations on the right. So let's look at our exercise and let's calculate, let's calculate the median for our right skewed data. Let's calculate for our right skewed data. Okay, let me make this bigger. So now I'm going to actually calculate. So I'm going to argue that the best measure of center is the median. And now we're going to calculate it. Note, when we compute statistics, we return to the original values of the data. All right, we don't use these numbers, remember, because we rounded these numbers. So I'm going to demonstrate using the original values here how we find the median. I've made it easy because what have I done here? I show half the values here and half the values here. So looking at this, what is the median? Do you know?
$21.
Okay,
The
so
median will be between 25 and 26.
all right, so
That's the same.
okay, so then we have two values in the center. We have two values in the center. One is 20.58 and the other is 20.89. To find the median, you actually have to average the two center values. That's right. So let's do that. Let's find the median by averaging those two center values. I'll bring those with me. I'll bring them with me. That didn't work. I'll just do it here. So I need to take the 25th I'm going to make it bigger. Oops, not easy. 1 minute. I'm just going to remember them. So 20.58 and 20.89. So 20.58 and 20.89 are the two middle observations in the ranked data. You know what I mean? Ranked, it's in order, right? It's ordinal, ordered. So we average, the median is the average of those two. And what do you get?
25.50. Oh no.
No?
Oh no, oh no.
Oh, okay. What do you get?
20.73.
Okay, so let's write the whole number down because there's more numbers, right? 20.735. 20.735. And I wanted to take a moment to mention about the digits here. Now, spending is in dollars and cents, so our answer should be in dollars and cents, correct?
Yes.
So how should we present this then? It's 20.74. Okay, so if I make lines like that, it means approximately, you know? So we round 20.74 to be precise. In general, though, I tell the students to keep 2 more decimal places than the original values. So you could keep as many as 4. And that's a rule that I use through my notes so you can follow along. Okay, and you'll read about it in the notes. So another note. Keep 2 more decimal places than the original values. It's just a rule I have for my notes so you can follow. So it's 20.74 is now the median. So let's see, where was it? That's going to be here. So whoever guessed here, very good. And the ones who guessed here, not bad at all. You're close, but we need to be a little bit more this way to account for the fact that there's a lot more data here too, right? So we want to be right in the middle. So that is going to put us 20.74 is really 21. So we end up here. So that's really the median in the data set. It's not an actual value, but it divides the data in half. So there's should be 25 here, 1, 2, 3, 4, 5, 6, 7, 8, 9, you know, counting, that's 25, and then this makes 25. I think it's, yeah, between those two, right? This one. No, I think it's over here because those are both going to be 21 in this data set. It will be here. 20.5 and 20.89. Let me go back to the data. I have to look at the data. Let's see, 20, yes, because this one is 20 and this one's already 21. So it's between these two that were rounded to 21 each. And it's in between those. So yeah, okay. So that's what a median is. Now the mean, let's calculate the mean just to compare because often data sets will give you both. I mean, if you use software, you'll get both. What is the mean of this data? How do I figure that out? I'd have to go to the original data. I'm just going to tell you, and then you guys can practice it. But if you look at the original data here, you have to add these all up and divide by 50. And what will you get? I'm going to have to check on in this data set here. Hold on. All my answers are here. Maybe I didn't put it here. Oh, I didn't. Nope, I didn't put it here because I just have the information on the median. Okay, so what I'm going to ask you, sorry. Oh, we'll talk about it tomorrow, so I'm going to leave this. So what should be the case? Is the median, should the median be less than the mean? Yes, that will always be the case. All right, I'm going to shrink all of this. And I'll get you the number tomorrow because I don't want to spend time punching that in. So it is the case that the median should be a smaller number than the mean. And that is in fact how a method of, if you don't have a graph, I'll put these notes here. If you don't have a graph, you could look at statistics to determine if a distribution is skewed. So for a right skewed distribution, it should be the case that the median is smaller than the mean. The mean should be over here closer to this tail or the extreme values. Oh, I want to make it smaller. Right. All right, so we've done 2. Let's go on to the next one. 3. The next thing we want to report is the spread. The spread of the data tells you about the variation or the variability of the numbers. In this case, you can begin by mentioning the range of values from the minimum to the maximum. What is the minimum value? Remember, you have to go back to the original data. The minimum is $2.32, so we're going to mention this here. And the maximum was what's the maximum? What's in the chat? But all all the decimals, everything, 69.49. The original values. Right? So that's the range of values. So we have the range of values, but we also want to know between that range, how is the data spread out even in between? So what we want to do is expand this understanding of what the median is. The median divides the data into 25 before and 25 after. Why don't I also get halfway in between the first half and halfway between the second half? And that will give me an idea of how spread out it is throughout the distribution. So what I'm asking you to do next for the spread, when the data are skewed, the shape is skewed, the center is the median, and then that also affects the spread. Your reporting of the spread depends on the shape. When data are skewed, we report what's called the 5-number summary. Now the 5-number summary is different from the 5 features. We're working on the 5 features here, but the 5-number summary includes the minimum, the 25th percentile, the 50th percentile, the 75th percentile, and the maximum. Do we have most of these values? We have the minimum already. The minimum was $2.32. Do that again. The 25th percentile, we don't know. Maybe I can move this over because these are. So I'm going to do like this. So this is $2.32. We don't know the 25th percentile. What about the 50th percentile? Do we know that? And then we know 69.49. We know the 59 percentile because we just calculated it. 20.74. So all we need to do is get this one and this one. So how do we find the 25th percentile? Let's go back to the data. Okay, returning to the data. What you need to do is find halfway through this data. All right, so let me show you now. The reason, it was easy for us to see that we had to go here for the middle. But if you didn't see, if it wasn't created so neatly for you.
The 13 observation?
Right, very good. So let me show how, let me show the others how we get that. So what we do is we go to we use this formula, n+1 divided by 2 gives the middle. So if you begin with all of your data, we had 50 observations here, right? So it would be 51 divided by 2 gives 25.5. That's how we knew that we had to go between 25 and 26 to find our answer, halfway in between. But what if we only have half the data? What if n equals 25? So we're going to use the first half and the same rule. And this is how you get 13th. So this calculation I'm making is just showing me the observation I need. It's not giving me the answer. It's just showing me the observation I need. So that's why you know this is the middle here. So this 13th is the middle here, and I can just look across the pond that will be the one here. How would you find it? You will count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So these are the 25th percentile because 25% of the observations are below it. And this is called the 75th percentile because 50 plus 25 or 75% of the observations are below it. So this is 14.35 and 33.8. Any questions?
Teacher, could you please repeat again for me the percentile? I don't understand that.
The percentile. Okay. So the 50th percentile is the observation with 50% of the observations below. So half. So this is why we pick the number between 25 and 26, because half is smaller. So that's why we call this one the 50th percentile. We average the two middle values. Then, so you understand that, right?
Yes.
Okay, now we're going to repeat, but only with half the data, just this column. With this column, there's 25 observations, and I want to go halfway. So how do I do that? Well, there's 25. I add 1. That makes 26. Divide by 2 is 13. That's the 13th observation. This is the position where half is below and half is above. So this is the trick. N plus 1 divided by 2. Even visually, you can see, just look visual, this is in the middle. That's what you want. You want the value in the middle of the data. You don't care about the numbers, you care about the position. Okay?
Okay.
And the same here, you care about the position, not the, I mean, you want the number, but the interest to you is the order and the position. So the 13th is the middle of this column, and 38 is the middle of this column. And there, 33.8, I mean. So this is called the 5-number summary. And you can get this out of Excel. However, I caution you that one of the only, if you get into very detailed statistics, you'll start to see different softwares calculate some things differently. But in basic statistics, most things are calculated the same with your calculator or using functions in Excel. Except this, for some reason, everybody has a different rule for making the 5-number summary. But the numbers are very similar. They won't be too different. The issue comes if you want the 25th percentile to include the value or not. And I think that's mostly in the calculations what happens. So let's try this. Let's see. I don't know if we can do this in Excel or if it's more complicated. Let's do that tomorrow, okay? So I'll hold off on calculating things in Excel tomorrow for this exercise. So we can just finish some of these easier calculations just together manually. So notice we didn't have to do anything with the calculator so far. All we did was this. This was the only calculation we had to make. Well, and then we made this simple arithmetic here to find out this is the middle. So if you can see it visually, use your visual cue. If not, you use this formula here. N plus 1 over 2 gives you the middle. And if it's not a whole number, it means you have to go between 25 and 26 to find the answer. All right. That's the spread.
Thank you.
And we're going to talk more about the 5-number summary later, but I just want to finish the 5 features before we go today. So that's 3. Let's make this a little bit smaller. That didn't work. Hold on. I have to do this little trick. So I can move things. I want to shrink this. It's not working. Okay, so let's go to number 4. Number 4 is gaps and outliers. Gaps and outliers. Do we have any gaps? Is there any class where there's no data?
Yes.
No.
Yes. 5.
This one. Oops, I was trying to erase. So there's no data.
I was watching in the original data.
Right, so in terms of the classes, there's a gap here. You see? No data. Which class is this one?
Gaps.
Right, there's no data in 55 to 59. There's no data here. This is a gap. Now that's important because it's a signal that you might have what are known as statistical outliers. I've been speaking about outliers very loosely as the values that are away from the pattern. But then when I drew this, I included its own peak, right? I included its own peak. And do it again to make it look smooth. So it has its own peak. So the question is it part of the rest? Does it explain something, or is it significantly outside that it explains something new or something else, something interesting? So there's a definition in statistics of what an outlier, an outlier is formally. And we're going to test that definition. We're going to use that to test these values that are extreme to see if they're outliers. So let me. Yeah, that wasn't so bad. Did I lose a number? I lost a number here. 20, it was 14.35. Okay. So how do we check for outliers? You check. Oh, let me write this in. I'm doing color coding. So first you mention the gap and then you check for the outlier. So the gap is so we suspect outliers. The original values that we suspect are outliers are the last four, correct? So we're going to take the last four values with us. So these are the outliers that are suspected. So how do we check? How do we verify if they're very bizarre or strange in statistical terms? What we do is we establish what is ordinary for data. What we do is we use this to help us, the five number summary. Notice this is the first value, this is the last value. Between here and here, we find 25% of the observations. Between here and here, we find 25% of the observations. Between the median and the 75th percentile, we find 25%, and then we find 25%. So for 100%, there's 25% in between each. What about the middle? How many observations between this, the 25th percentile, and the 75th? How many observations between these two values?
$25.
Between this one and this one.
$27.
Keep going. It's okay, so it's 25 between here and here and 25 between here and here. So it's a total of 50%. So between here and here are half of the data inside. Okay, between the extremes, usually we find extreme values, there's 50% of the data between these two. So what we're going to do is say, let's call this the regular portion of the data between here and here, and verify if the rest of the data are reasonably close using this as a range. We have this a special name for this one, the range between here and here, because, okay, what is the range? I showed you here, this is a range of values, but you could calculate the range. What is the calculated range? So compute the range, calculate for all of the data, what is it? So this max minus the min, what do you get?
Max minus min.
Yeah, what value do you get?
67 point something.
So at this point, you should have either on your calculator, I mean, on your phone, you should have a calculator or manually making the calculation. I'm not asking for too much. So 67.17, right? Now I want you to calculate a different range. I want you to get the interquartile range. I have to change pages. So the interquartile range is equal to Q3 minus Q1. What is Q3? Q3 is the third quartile, and Q1 is the first quartile. What am I talking about? What are quartiles? Another name for this is, going through all the terminology, this is called the 75th percentile. And this is the 25th percentile. These all mean the same thing. So 3/4 is 75, right? And 1/4 is 25. I refer to these as Q3 and this one as Q1. Now, what were the values again? The third quarter was 33.80, I think. Let me go back. It was 33. Oh, I'll take this with me. That's all I need. I just need this with me. So that's our 5-number summary. This was the min. This is the max. This is Q1, Q2, Q3. So Q3 was 33.80 minus Q1 is 14.35. What is the interquartile range?
$19.45.
Very good. 19.45. So this means that the middle data, the 50% in the middle, is spread out by 19.45, a range of $19.45. So what we're going to do visually, I'm going to grab, I drew this in the notes. I'm going to take it from the notes because I think it's better than me doing it here without a ruler. Give me a moment to find it. Oh, it's here. There it is. There it is. Okay, so this is my okay, so what I'm doing here is I'm putting, this is the number line. And my data starts at $2. This is min, $2.32. And then on the number line, then there's $14.35. and 20.74, and then 33.80 and 69.49. So I put it to scale as much as possible, and then what I do is join that. So this is actually the box plot, but on its horizontal axis. If I took this and I flipped it, you see, it looks like the box plot. Okay, so the box plot is made up of the 5-number summary. And this range in here is known as the IQR. And we got the value 19.45 as the IQR. Now what we're going to do is use this range, but a little bit longer. From the edge here, I'm going to expand from this edge, Q3. Oh, I didn't take my, anyway, it's okay. I'm going to expand, I'm going to say values close to the middle 50% will be considered usual or predictable or normal or not outliers, in other words. So if you're here or in a little bit more, let's go a little bit more. The same with this other side, but there's no outliers on this side. I don't really have to worry. It's just there's some values that are very extreme out here. So what I'm going to do is I'm going to extend this and a little bit more. So what I'm going to do is make it IQR this is an IQR times 1.5. How much is that? So 19.45 times 1.5. So this is actually the rule. This is called the IQR times 1.5 rule. I'll highlight it. What value do you get for that? What do you get? Right, 29.175. So I'm going to keep these values until I'm finished, okay? So I'm going to make another note. As much as possible, do not round intermediate calculations. You keep it. Now, what are we going to do with it? What we're going to do is we're going to expand this a little bit more. So instead of using IQR 19.4, I'm going to use IQR times 1.5, which is really 29.175. And where do I end up? So it's going to be this, but a little bit more. So I'm going to put this and a little bit more. How far will I get? So what is 33.8 plus 29.175? You get to 62.975. So that puts you like, I'll use a yellow, puts you like here. So this is IQR plus a little bit more. IQR, sorry, it was about here. And then plus half of it, right? So 1.5. And that puts you here to this value. So what is this value? This value is the threshold. Any values beyond 62,975 are outliers. That's the rule. Technically speaking, statistical outliers, not just observational anomalies. So out of the values that we have here, how many of them are outliers?
Three outliers.
There are 3, right? Not this one. This is considered close enough. It's these 3 that are outliers. So this is the technique called the IQR times 1.5. You need to add it to the end of the interquartile range. Now this is for a right-tailed distribution. If you were to go this way, you have to subtract from Q1, this one here, and go this way. But we went this way for a reason. Anyway, you get to practice in the notes. There's you'll see. So this is the rule. It's called the 1.5 times IQR rule. Let me show you in the notes so you feel better. So I'm going to go back to where I was to find this. Here's the rule. I don't know if that helps, but that's the rule. It's the 1.5 times IQR decision rule. And this is the best way to see it. Observations are statistical outliers if they fall outside of this range. Q3 plus 1.5 IQR or Q1 minus going left on 1.5 times IQR. That's the rule. And we call them statistical outliers specifically, not just curious observations. All right. And this was on page 16. All right, so we have found 3 outliers, and this is what would have to go into our report. So I did all the calculations here, and I will copy them back to my report.
Can I have a question?
Yes.
Can I see, or you can find the outliers?
Oh,
I saw the 3 outliers, but all you can recognize them.
Okay, you can recognize them. You can recognize them because they are above this number. And this number was computed.
Okay.
It was computed by 3380 plus 29.17. That's how I found it. And this is the threshold above
okay.
which all the
This
outliers are.
This is okay.
Okay, good. I know it's hard to write and follow at the same time, but you'll get it. So let me take these with me back to my report. And I put it here. I put it here. Actually, I can just erase this one. So these are the 3 outliers here. Actually, no, because those were suspected, but we ruled out this one. This one was not an outlier. Okay, so there are 3. So 3 outliers.
Outliers.
By the
Suspected.
1.5 times IQR test. Okay, so the outliers are suspected, but this was the conclusion. And that's that. So number 5.
Thank you, Roxanne.
Sure. So the 5th feature before we go tonight is peaks. Tell me about the peaks. Well, actually, you know what? I'm going to let you go, and tomorrow this is where we're going to start. I want you to tell me what the peaks are, okay? So that we identify 3 peaks, and you have to tell me the center of the peak, the class of the center of the peak. And that's what we'll start with tomorrow, all right? Also, I'll show you how to calculate these things in Excel. And that is it for tonight. Okay, do you have questions?
Thank you.
Okay, no questions?
No, it's clear.
I think I missed the explication for how to suspect the outliers.
Oh, to suspect the outliers, it's values
Yes.
that
That's
are far
up to-
away.
to
Just far
identify.
away. Yeah, to identify, you say just have to be far away. The gap
Okay.
and far away from the rest. So that's why I suspected 4, but I only found 3 in the end.
3. Okay. Okay.
So I'll leave you with that question. And we'll meet tomorrow at 9:30, right?
Thank you.
All right.
Yes.
Thank you very
Okay.
much.
All
Good
right.
night.
Thank
Good
you.
night.
Good night.
Thank you.
Thank
Bye.
you.
Bonne nuit.
Okay.
Bonne nuit.
Bonne nuit.
À demain.
À
À demain.
À demain.
Okay.
Ma fille m'a dit de parler français, n'a dit,